A Kafka broker in Kubernetes kept crashing with out-of-memory error every 6 hours. The team assumed a memory leak, but the real culprit was a misconfigured retention policy. Segments accumulated faster than the cleanup interval could handle, filling the disk and triggering an OOM. Let's break down why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover Kafka and the distributed log. Kafka is a distributed event streaming platform built around a distributed log, an append-only, partitioned, replicated commit log. It provides durable, ordered, and fault-tolerant message storage, decoupling producers from consumers. At its core, Kafka's log is an append-only sequence of records. Each record has a unique offset within its partition. The log is split into segments, files on disk that are rolled over when they reach a size or time limit. Sequential disk writes are orders of magnitude faster than random writes. This Java class simulates Kafka's log segment behavior. When a segment reaches its max size, it rolls to a new file. Each partition is a directory with multiple segment files. Partitions are the unit of parallelism. Each partition is an ordered log. Producers write to partitions based on a key. Within a partition, messages are ordered. Across partitions, order is not guaranteed. Use the entity ID as the partition key to maintain order per entity. This producer uses the user ID as the partition key, ensuring all events for a user go to the same partition, preserving order. The AX equals all setting waits for all in-sync replicas to acknowledge. Kafka replicates each partition across multiple brokers. One broker is the leader, the rest are followers. Producers write to the leader, and followers replicate the data. The min.insync replicas config determines how many replicas must acknowledge a write for it to be committed. This command creates a topic with replication factor 3 and min.insync replicas equals 2. The describe output shows the leader, replicas, and in-sync replicas ISR for each partition. Consumer groups allow multiple consumers to read from a topic in parallel. Each partition is assigned to exactly one consumer, ensuring ordering within a partition. When a consumer joins or leaves, a rebalance triggers and partitions are reassigned. This consumer uses manual offset commits after processing each batch. Enable auto commit equals false prevents data loss on crash, ensuring at least once delivery. Idempotent producers prevent duplicate records caused by retries. When enabled, the broker deduplicates based on producer ID and sequence number. The performance cost is negligible, so always enable it in production. This producer enables idempotence and uses batching with batch, size equals 16 KB, and linger, ms equals 5 to improve throughput. Compression with snappy reduces network bandwidth. This is the same issue we highlighted at the start. Here's exactly why that happened. The topic had log, retention, bytes equals 1 GB, but log, segment, bytes equals 1 GB and log, retention, check interval, ms equals 300,000. With high throughput, segments accumulated faster than retention could clean them, causing the log directory to grow beyond the container's disk limit, which triggered OOM as the OS tried to page. The fix was to align segment size, retention size, and check interval with throughput. Setting log, retention, bytes equals 500 MB and log, segment, bytes equals 256 MB, ensured segments are cleaned before disk fills. Adding disk monitoring prevents recurrence. With 10,000 partitions, the OS struggles with file handles and page cache, killing sequential I/O advantages. Keep partitions per broker under 4,000 for high throughput. If the number of in-sync replicas drops below min.insync replicas, the broker stops accepting writes. This happened when a broker went down for maintenance and the team forgot to adjust min.insync replicas. This is the exact misconfiguration from the incident. With both retention and segment size at 1 GB and a 5-minute check interval, segments accumulate faster than cleanup, leading to disk pressure and OOM. If you use auto-commit, offsets are committed periodically. If a consumer crashes after processing, but before the next auto-commit, messages are lost. Always use manual commits after processing. If you set maxin flight requests per connection 1 without idempotence, retries can cause out-of-order writes. Always enable idempotence to maintain ordering. The article references ZooKeeper for controller election, but Kafka 3x KIP 500 replaces ZooKeeper with KRaft KafkaRaft. If you're deploying Kafka 3.3+, you can run without ZooKeeper, reducing operational complexity. However, KRaft is still maturing. For production, many teams stick with ZooKeeper until KRaft is fully stable. The article mentions cooperative rebalancing, but doesn't show the config. Use partition, assignment, strategy equals org, Apache, Kafka clients, consumer, cooperative sticky assigner to avoid stop-the-world rebalances. This is critical for large consumer groups. The article mentions compacted topics for state stores, but doesn't explain log compaction. With cleanup, policy equals compact, Kafka retains only the latest value for each key, enabling key-based lookups without scanning the entire log. This is useful for building materialized views or caching layers on top of Kafka. To debug consumer lag, run Kafka consumer groups describe. To check ISR, use Kafka topics describe. Monitor disk usage with df. Align retention and segment sizes with throughput. Let's run through some common interview questions. How does Kafka handle broker failure? Controller detects failure, selects new leader from ISR. When to choose Kafka over RabbitMQ? Need replay, multiple consumer groups, high throughput. What happens if consumer crashes after processing but before commit? Message reprocessed at least once. And a few frequently asked questions. How is Kafka different from a message queue? Kafka is a distributed log. Messages are stored durably and can be replayed. How many partitions should I start with? 3x expected consumers, monitor lag, double if needed. How to prevent data loss? Enable idempotent producers and manual offset commits. To recap, Kafka's distributed log is an append-only, partitioned, replicated commit log. Always use idempotent producers and manual offset commits. Choose partition count wisely and align retention settings with your throughput to avoid disk pressure. Ready to go deeper? Up next, MapReduce and batch processing, then stream processing, then inverted index and text search. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.